Now that we learned how enols and enolate ions are produced, we will have a closer look on how they can react with electrophiles. Enols are nucleophiles and they react with electrophiles to introduce a new group at the carbon atom in alpha position. And this reaction starts with a lone pair of electrons on the oxygen atom, which attacks the electrophile through the carbon-carbon double bond. You can see this here. So we start with the enol, and then the lone pair of the oxygen goes down, and hereby the nucleophilic attack is conducted by the carbon-carbon double bond. In the subsequent step, the positively charged oxygen atom of this intermediate gets deprotonated, and hereby the alpha substituted ketone is formed and a proton is released. And as you might already see, this first step, so the nucleophilic attack of the carbon-carbon double bond, is very similar to the mechanism we saw for the reaction of alkenes with an electrophile. However, enols are stronger electrophiles compared to the carbon-carbon double bonds. In organic synthesis, the reaction of enols with electrophiles is commonly used in order to introduce a halogene in alpha position of an aldehyde or ketone. And as this reaction is quite important in organic chemistry, we will now have a closer look on the reaction mechanism. And we will have a look on the bromination of propanone. And propanone is also called acetone. And this reaction is conducted with one equivalent of bromine and an acid catalyst in a solvent such as water. At the beginning, the keto form of acetone is in equilibrium with the enol form according to the acid-catalyzed tautomerism. And as we just learned, the acid-catalyzed tautomerism starts with the protonation of the oxygen atom of the carbonyl group, followed by a deprotonation in alpha position to form the enol form. So in principle, we have this first step and the second step, which is then combined in the acid-catalyzed tautomerism. So we start with this ketone, which is our acetone. Then the first step is the protonation of this oxygen atom of the carbonyl group. Then we form a positively charged intermediate, which gets deprotonated by water, and we end up with the enol. Important to see is that here is only a small amount of enol formed as the equilibrium is on the keto side. Then in the next step, the bromine molecule approaches the enol, and hereby the bromine gets polarized. And then the enol reacts rapidly with the polarized bromine, and hereby one bromine atom is introduced in alpha position and an oxonium ion is formed. Then in the last step, water acts as base, and this oxonium ion gets deprotonated to form the bromopropanone or bromoacetone. And very important, if you count the number of alpha hydrogen atoms, you can see that propanone has 6 alpha hydrogen atoms. Now you might expect that we then end up with a mixture of various brominated products. However, the bromination with one equivalent bromine is very selective and you will not get a mixture of various brominated products. And the reason for this is that the bromine has a strong -I effect, which reduces the basicity of the oxygen atom of the carbonyl group. Accordingly, it is more difficult to protonate the oxygen of bromopropanone compared to propanone. And therefore, the rate of the further bromination is decreased and we selectively form only the monosubstituted product. Now we continue with the reactions of enolate ions with electrophiles. An enolate ion is formed by deprotonation of an aldehyde or ketone in alpha position in the presence of a base. And this can be seen here. So we start with the ketone or aldehyde, then we have a base around so that this base deprotonates the hydrogen atom in alpha position. We form the enolate ion. And the enolate ion is doubleized by resonance, and the major resonance form has the negative charge at the oxygen atom. And this resonance stabilization explains also why the alpha hydrogen atoms of aldehydes and ketones are relatively acidic. So enolate ions are strong nucleophiles, and due to their negative charge, they react faster with electrophiles compared to enols. And enolate ions have 2 electrophilic sites. This is shown here. So you can have either negative charge located at the carbon atom or at the oxygen atom. That means in principle, the enolate ion has two possibilities in order to react with an electrophile. However, the reaction of the electrophile on the carbon atom is more common. So it is preferred to go in this direction. And similar to enols, enolate ions react with halogens to introduce an halogen atom at the alpha position of an aldehyde or ketone. And in the past, this type of reaction was used to identify a methyl ketone group. Therefore, the unknown compound was treated with an excess of both hydroxide ion and iodine. And always, if a yellow solid was formed, the presence of a methyl ketone group was confirmed. This yellow solid is iodoform, and therefore this reaction got the name iodoform reaction. So let's have a closer look on the reaction mechanism. The reaction starts with the deprotonation of the methyl ketone in alpha position by the hydroxide ion. So this is a methyl ketone group. We have a methyl group directly connected to the carbonyl group, and then the hydroxide ion deprotonates one of the alpha hydrogen atoms. Hereby, an enolate ion and water is formed. Subsequently, the iodine approaches this enolate ion, and hereby the iodine gets polarized. Then the nucleophilic attack of the enolate ion at the partially positively charged iodine atom forms the monosubstituted product, and this product is also called monoiodoketone. Now we have one iodo atom in alpha position. This iodo atom has a very strong minus I effect and hence makes the remaining hydrogen atoms in alpha position more acidic, which in turn then favors the reaction with hydroxide to form an enolate ion. Hence, the reaction is not yet finished, but continues with another deprotonation in alpha position, followed by the reaction of the enolate ion with the polarized iodine to form the disubstituted ketone. This is shown here. So we do more or less exactly the same reaction, just with one iodo atom in alpha position. So again, the hydroxide ion deprotonates another hydrogen atom in alpha position. Then we form this enolate ion and water. Another iodine molecule approaches this enolate ion, and hereby the iodine gets polarized, followed by the nucleophilic attack of the double bond. Hereby, we form the disubstituted ketone. Then we have two substituents of iodine at the alpha position, and as both iodine atoms have a strong minus I effect, the remaining hydrogen at alpha position is now even more acidic as before. Accordingly, another round of reaction cycle starts. So again, we start with the deprotonation of the remaining hydrogen alpha position. Then we form an enolate ion and water. An iodine molecule approaches again, and we have a nucleophilic attack of the carbon-carbon double bond to this polarized iodine molecule, and we will end up with the tri-substituted ketone. And then the reaction is still not yet finished. And the next step, the hydroxide ion acts as nucleophile and attacks the carbon atom of the carbonyl group. Hereby, an alkoxide ion is formed, and this alkoxide ion further reacts in order to regenerate the carbonyl group, and hereby the triiodine ion is abstracted. And the reason why the triiodine ion is abstracted and not the hydroxide group is that this triiodine ion is a better leaving group compared to the hydroxide group. And in this step, a carboxylic acid is produced. Finally, in the last step, the triiodine ion deprotonates the carboxylic acid, and hereby triiodomethane and carboxylate ion is formed. And you can see here we have an equilibrium, whereby the equilibrium lies on the side of the triiodomethane and the carboxylate ion. And the reason for this is that the carboxylate ion is stabilized by resonance and hence more stable than the triiodine ion.